Okay, DBF files. DBF files are, they were a format, a database format that originates with DBase, a relational database program called DBase, which is what I did my master's database course on 20 years ago, whatever it was. Okay, so sometimes you come across these DBF files. You may be familiar with them when you look at your shape files. Remember, .dbf is one of the files that goes with the shape file. So it's the database format where the attributes are stored in a shape file, stored in a .dbf file. So they took this old DBase table format and used it as part to store the attributes of shape files. Anyway, I have a little table which is the ecology of the fish, where the fish lives. It's got information on the ecology of my fish species in a DBF file, and I can also use the QGIS, the same QGIS vector import facility to import a non-spatial table as well as spatial tables. It doesn't sort of suggest that it can import non-spatial tables, but you can. So that's how I did it. Equally, I could have exported my DBF out of Excel as a CSV and loaded it up as a CSV like we've done for aspatial tables in the past. But this was just a way of actually going directly from the DBF file into a spatial table. And there it is. There's my ecology table, which just has 3 columns. Unique identifier, the species code, and some of them have descriptions of ecology as well. Also note, when I imported this table, there's another thing. Always look at your data. There was a line got imported with no data on out of my DBF file, which wasn't in my DBF file. So my DBF file didn't have this line, extra row in with empty row. I import it as an empty row. Always check what's happened. I think this is just showing that you can highlight the form and you can get the tables and you can get information on the tables on the right-hand side. I think that's all that stuff. Okay, Spatial SQL. So we've got our data in finally. Let's do some querying on it. So what is Spatial SQL? It's simply SQL statements that undertake some kind of spatial query using the PostGIS functions or operators. We'll meet those in a minute. So we can do things like query vector attributes, length, area, perimeter. We can do overlay, intersect overlaps within operations, and vector distance queries. So your standard collection of vector spatial analysis functions. So I want to know the length of each of my river lines. Remember, I imported one set which is the basins, the river basins, the polygons. One is the river lines, and the other is the points where my fish are. So I can just do select the name of the river, and then I can use the st_length PostGIS function on the geometry field of my rivers table, and I'm returning it as an alias length meter from river. So I'm saying, get the geometry of the line, return me the length. Yep. And that will be in the units of the coordinate system that's defined for that rivers, which is Lambert conformal conic, so the values are in meters. So here we go. We can see that the length of the river lines are returned as rather long decimal point numbers. We can also see that only some of our river lines actually have a name associated with them. The Rio Pernas, the Renes Sucil, most of our lines don't actually have names. So that it's that easy to get the length of a line. And I can start writing more complex queries to return other sets of data. So if I want to know the 6 longest named rivers in my database. So first of all, I've got rivers that don't have names. The other thing is that a named river may be made of more than one line. So we've got this 1-to-n relationship between river names and river lines. So I need to group the function. So I need to do a grouping online. So again, I return the name of the river. I want the total length of that river. So I want to sum all the lines, sum all the lines, the length of all the lines for that each river. From river, where the name is not null, I'm not interested in returning lines, the sum of lines that don't have names, because they're for lots of different rivers that are scattered all over the place. So I don't want when the name is null. I'm going to group by the name because I want to sum the length of all the lines for each river name. I'm then ordering them by my sum length geometry. Unfortunately, PostGIS, I really wish I could just do length m in the order by function, but it doesn't allow that. You have to write the full sum length there, and I've got a limit to return the first length. I saw a couple of quizzical looking looks there. Has anybody got any questions about that query? Is everybody happy with that query? It returns the 6 longest rivers ordered from the longest to the shortest, yes. So I'm doing a group function. I'm summing the length of all the lines where the name, where they have to share the same name, as long as the name is not null. That's giving me the length of the 6 longest named rivers. Yes? Sorry? It would, well, first of all, it would instantly throw an error because you were using an aggregate function within without a group by function. You can only have an aggregate function like sum or mean, average, when you have a group by function, because you have to aggregate on some kind of field value. So that's the answer, is it would fail. But if you took out sum and just had st length, and you took out length by geometry there, you took out that, and you took out the order by, it would just list all the lines. It would effectively just list the longest 6 lines, named lines. That's what it would do. So you might get 3 lines for the Rio Lerma and 1 line for the... Okay, clearly from a presentation perspective, this data is, as I said, it's the scale of thousands of kilometers. There is no way that we know the length of the line, the length of a bit of river, to what appears to be about 1/10,000,000th of a meter length. It's just absurd, but it's just an artifact of the number of bytes used to store bits of information in the computer and the division and the sums that are done on it. So if I was to report this, it's absolutely balmy to put these figures into a report. In fact, if I was to report these, I would probably round them up to at least sort of 10-kilometer lengths, probably. Even a kilometer is probably a bit ambitious at this kind of scale. Nevertheless, just for principle, I think we've probably covered all this as well, but if I want to get a more reasonable result to put into a report, I want to round my results, I can wrap my sum function in a round function to do a rounding, and comma 1 to return 1 decimal place to round to 1 decimal point. Also notice that I am this double colon numeric. I think we've met this problem already. It's called casting. It's basically converting one data type into another. Now, why do I have to do this? St length, you have to look at the parentheses of this. So st length, which goes from here to here. So the st length, sorry, here to here. So st length returns a double precision data type. Round only accepts numeric data type, but not double precision. Don't ask me why. It just is. It's the way of the world. So length chucks out double precision, then you're trying to pump that into round, but round doesn't take double precision, it only takes numeric. So we have to cast it to numeric to pump it into, before we can pump it into the round function. Annoying, but that's the way of the world. And there we go, we've just rounded to 1 decimal place. In fact, we've done it to a kilometre. I've now divided by 1,000 this time because kilometres is a more reasonable reporting unit than metres at this kind of scale. So I divided by 1,000 to get it into kilometres. So this is 510.5 kilometres. Far more sensible figure to present to somebody than 51,000, 510,000, whatever metres, point whatever metres. So report things at sensible units and think about the accuracy of the data that you're reporting on when you decide how many decimal points or what rounding you're going to do do the report. Don't report ridiculously over the precise figures that are meaningless. All right, so that was length. Area of a draining basin. Okay, some of these are in Spanish because it's Mexico. So the nombre, the name, we're returning the basin, the name of the basin being just the geographical area that drains into a river system. We're selecting from the basins table, which is a polygon table, the geometry field, which stores the polygons, and we use the st area function. Again, we can round it, we can cast, and in this case, we're dividing by 1,000,000 to get area in kilometres squared rather than metres squared. Okay, now I'm just putting a note there. Because of the syntax, I was getting a syntax error. Okay, so if we look at this, we've got geom is the internal syntax. Then we have the st area. Oh, yeah, that's that one. Now, the only way I could get this casting to work was to put a parentheses around that part of the equation to then be able to cast to numeric. So it was a little tricky to just get the syntax correctly, and I had to add in an extra set of parentheses that I didn't think I would have to until I actually tried to write the query. So bear that in mind. Sometimes you might have to embed things in an extra parentheses there. Okay, so that's area. It's that simple. Okay, operators. So operators are syntax so remember operators, things like equals, greater than, less than or equals to. Those are operators in an aspatial database. Operators in a spatial database, there are two types of operators defined. There are distance operators and bounding blocks overlay operators defined. So the double ampersand, for example, returns true if two geometries bounding boxes intersect. So there's a whole set of operators relating to bounding box overlay, basically. There is also a set of operators further down here which are to do with distances, returning distances between geometries. Let's see some of these in action. Let's start with distance. So this operator, which is a greater than, then a hyphen, then a less than, or a less than, then a greater than, a hyphen, and a greater than, returns the distance between geometries. So I want to know how far each of my fish observations is from Mexico City for some reason. The logic of it, let's not ask about it. Great deal. Okay, so so this is measuring the distance from where I've caught a fish to Mexico City. So I first need to define Mexico City, and I'm defining it as a point in the center of Mexico City, just the figures I got off Google when I said coordinates Mexico City. Okay, now it gave me the coordinates in latitude and longitude, WGS 84 presumably. Okay. But my data is in Lambert conformal conic. So I can create the point. So here's the point, the coordinate for Mexico City, the longitude, the latitude in WGX 84. Remember, stgeom from text, I create my point in WGS 84. I then need to transform that point into Lambert conformal conic projection. Yep. Okay, remember? So I then use the st transform function to transform this geometry defined here to my coordinate system that I added my Lambert conformal conic projection. Okay, what does that do? ST transform, remember, it chucks the transformation out to the proj4jc library, which then returns us the result. So the result gets returned into this function. And we want to find the distance from each of our fish locations, g.geom, Gudaids being the table with the point fish locations. We want to know the distance between that point geometry, and there's the distance function, to this location, which is the location in Mexico City, transformed from WGS84. Okay. This is without it rounded. This is the equation if I'm rounding the results to integers. Okay. I just thought that was probably easier to understand than, it gets more complicated the more things you add in. This is the result we get. So from location 1, fish location 1, the distance in meters to Mexico City is 5,344.3. Okay, that's how I get. That's how you use an operator for distance. Really quick, easy. A common thing to know in the work that I do is how far is each point location where we've sampled a fish from some other location where we've planted a fish. So I sampled a fish, found a fish. Why are we interested in this? Is because we're interested in the genetic diversity of the fish. The further organisms are from each other, the more genetically different they tend to be. Just like humans. You pick a random human out of somewhere in Central Asia, they will be more genetically different to me than if we picked a random human being out of 100 down in Kingston Town Centre. On average, I hasten to add. So we're interested. One of the things I'm interested in is what's the correlation between how different these fish are genetically and how far they are apart from each other. So I need to know how far is one sample from another sample. All my samples are in one table. So this is an example of a self-join. This requires a self-join. I want to join all my fish records onto all my other fish records on the basis of their spatial location. Sorry, I don't want to join them. I want to calculate the distance between all the points, all combinations of points in the table. So I need one version of the table and compare it to the other version of the table. Except where the rows are the same in each table. So I'm going through, so I've got two copies of the table. I work my way through the first table and I go to the first record and I measure all the distances to all the records in the second version of the table except the one for the one that I'm looking for. Then I move to the second row in the first table, do exactly the same on the second table, etc., etc. So in the where function I can use, so I have where the ID, unique ID, is not the same in the two versions of the table. And as you can see here, I can just return the ID of the first observation, the ID of the second observation, and then I can use the distance function operator to calculate the distance between those 2 points. And I get a table which gives me all pairwise distances between pairs of points in a table. Quite a useful thing, useful for things like transport matrices and things like that as well. All these triangular tables that you see for distance between various cities or something like that. That would be done in the same type of query. So that's distance. All right, spatial overlay. Two types of spatial overlay, bounding box operators and spatial overlay functions. So remember operators, so we've done these, we've only looked at one of these distance operators. We're now looking at these bounding box spatial operators, then we'll look at true spatial overlay. So the double ampersand is a 2D bounding box intersect. We're familiar with what a bounding box is, yeah? We just get the geometry, we put a box around the geometry. Why do we interested in bounding boxes? Well, because they're really quick to search on compared with searching on full geometries. So quite often, sometimes particularly things like sort of metadata search engines, portals where you're getting a sort of searching through large amounts of data, doing a bounding box is often a lot more sensible than doing a full spatial search. And indeed, bounding box searches are usually done before any full spatial search because they sift out lots of records that you don't need to do the full mathematics on. So they have a function in that respect as well. Okay, so I want to know how many river lines, or how many bounding boxes of my river lines intersect the bounding box of the Mexico City basin. So one of those basins is Mexico City, the bounding box around Mexico City, then I've got all my lines and I've got the bounding box around each of the lines, my river lines, which one of those intersect each other. So I can do that with this query. I've just selected the count, I've just counted the number of them from rivers and basins where the bounding box of the river geometry bounding box intersects the basin boundary box. And in this case, the basin name is Lago Texcoco, which is actually the Lake Texcoco, which is the lake that used to exist where Mexico City existed now. And indeed, I get 23 lines, river lines that intersect. That's the result that I get. How do I know that's right? Keep emphasizing this for you. Check it's right. So many times in my life, I've assumed something is right and I waste a lot of my effort as a result. So how do we know it's right? Well, the best thing is to view the solution on a map. How do we view spatial results of queries on a map? Well, we can use QGIS. Now, so if I want to view the result of a query in QGIS, I create a view. Remember, views are saved queries which can be used as tables in other queries. So I use the create view syntax. I'm going to create a view called Mexico bounding box rivers as I'm selecting R star, so I'm returning all the rows from river that includes the geometry column. Okay, so I'm just returning, I must return a geometry column because I want to display it on a map. So I'm returning all the rows from river, all the columns from river, where the river geometry intersects. So it's just the same query embedded within defined as a view. And then I can, in SQL, select star from Mexico City bounding box rivers, the view. That's the data that's returned in the table. Okay, what do I do? Well, I just connect in QGIS. I just connect to my database like I did for loading data. And then I can add, we can see, look, there's our Mexico bounding box rivers listed as a table, spatial table that we can load from PostGIS. There is one important thing to notice, though, is that when this adds up, because views don't have primary keys, okay, they may include the results of fields from the primary keys, but that doesn't mean that just because a field is a primary key in a table does not mean it's going to be a primary key of a view that uses that table. There's no connection between them at all. So there is no primary key defined in this table. QGIS has trouble because QGIS needs a primary key, or at least needs a unique identifier to be able to display the spatial data on the map. So as you can see here, what you get is an empty field, and you have to make sure that you output, your query outputs a unique identifier, a unique field. It doesn't have to be defined as a primary key, but it has to be a unique value. In this case, the ID field is unique, and I have to physically select this and set it as an ID field in the load window for QGIS. Otherwise, you can't load the data up. So bear that in mind. Right, so I select that, and woe behold, well, there we go. Okay, we can see our rivers. Here's Mexico City drainage basin. It's a closed drainage basin, or it's it should be closed, but it isn't anymore. And we can see that we've got rivers that are outside of the region, of the boundary, but because it's the bounding box, it's the intersection of the bounding boxes of these geometries, they're included in their result. I'm not going to go through any of the others. Look at the other spatial operators. They do similar things slightly differently. So true spatial relationships are, you require spatial functions to undertake them. So I'm not going to go through these. I'm presuming you kind of know these, and if you don't know them, we'll go and look them up in detail. So these are some diagrams, schematic diagrams that are meant to show the sort of different relationships that can exist between the different geometries. So the equals relationship is saying, is a polygon the same, are two polygons exactly the same, are 2 points the set exactly the same, are 2 lines exactly the same. I don't like these, but I haven't found out with the better and better diagrams yet, but I'm sure some could be drawn. Overlap, whether things overlap, lines overlap, sets of points overlap. Whether something is within or contains their inverse relationship of each other. So in this case, a point is contained by a line. In this case, a line is enclosed, contained by a polygon. Okay, so there's contains, within contains relationships. There's also intersects relationships. Here's a line intersecting a polygon. And the disjunct relationships are no part of the geometry share the same space. That would be a disjunct relationship. Intersects is kind of the opposite, at least what they share at least one point in common. So say, look up the definitions of these if you're not familiar with them, exactly what the difference is. Touching is about contact with the outside of spaces rather than the inside of shapes. Crosses, now what's the difference between a touch and a cross? Well, yeah, obviously a cross involves part of it being in the interior of a polygon, whereas a touch is just the edge of a polygon. So not all these, so some of these between different geometry types are effectively equivalent. So let's think a cross and an intersect on two pairs of lines may be the same. Okay, look those up. So those kinds of true spatial relationships. Yes? Intersect and cross. Told you not to ask difficult questions. All right, intersect, let's have a look at that. Yeah, well, they may be exactly the same result for the geometry types. I'm just having a look there. So an intersect, as I say, I would have to look up the definitions exactly of each one. So intersects must at least share one point. That would be intersect if I remember correctly. Crosses, I suspect, requires both an internal and a edge point. But that crosses doesn't really count for things like a point. A point can't cross a line. It's either on a line or not. So the crosses relationships between points and lines is the same as the intersect relationship between points and lines. But you can see that the crosses relationship between polygon may not be and a line may not be the same. So a line that's stopped, if that stopped on the barrier, that would be an intersect, but it would not be a cross. That would be a cross, I think. Yeah. I have to look these up in detail every time I want to be 100% sure about the relationship. Okay, so overlay functions. Overlay functions do true spatial relationships between geometries. There are two sets of functions. There are functions that return true or false depending on whether the relationship is met or not between a pair of geometries. And there are geometry processing functions that return the parts of the geometry that meet the criteria. Okay, so you're either returning true or false, this spatial relationship exists or doesn't exist, or you're returning the intersected geometry that makes that true. Okay. I want to find the river lines that are within a polygon, basin polygons. Okay, I want to see which polygon is each line within, basically each river within. So I can select I'm just returning, so the river ID, the identifier of each river line. Then I'm returning whether the river geometry is within the basin geometry. as within, and the name of the basin. So that's it. So I'm returning my river number, my unique number for my river. I'm returning a true or false value as to whether it's inside or within the basin or not. False. So this river line 83 is not in the Laguna, excuse my pronunciation. Yeah, we got two experts. I would just, wherever, the Rio, I should never work with Mexican fish because they have these huge, great names in local languages, never mind Spanish. I can't pronounce any of them. The Rio Mesquital. So this river line is within the Rio Mesquital. It's not within these other, has no spatial relationship with these other polygons. I hasten to add here that a river line could easily, well, no, it probably couldn't be within two different ones. It depends what the definition of within is. So if a river line had a point which was on the boundary between, say, the Mesquital and the Pinoco, would it be true in both of those or not? It depends on what the definition of within is. But anyway, this is giving us a pairwise list, all the lines and each of the basins and whether it's true within or not, that basin. Okay. Now I want to know which basin is each observation within. So this is a point within polygons. This is a nice, easy one, very simple. But instead of returning true or false, because that results in a table that's got T's and F's for every river line basin combination, and if I've got thousands of river lines and hundreds of basins, we could be talking millions of lists. Really what I want is just where each observation, which one basin each observation is in this case. So I've got the observations, the species, I'm returning the name of the species as well, and the basin. And in this case, within the where clause, I'm returning only rows where the fish geometry, the point geometry, is within the basin area polygon. Okay, so I can see that observation 572 is of A Tauri, and it's in the Laguna, this lake, whatever that is. Okay, and we can see that only these points should only be within one polygon. Okay, so it's telling us which record is within which basin. Slightly change that round. So if I was asked which basin does each species occur, so subtle difference in question. So this one is which basin is each observation in. So the emphasis or the focus is on the observations. We're just asking it the other way round, which basin is each species in. So in this case, we've got lots of records for each species. So we need to group those by the species, or at least get only one record for each species in each basin. And we can do that with a distinct. So I'm returning the species name and the basin name, where the geometry of the species is within the geometry of the basin. I only want unique combinations. I may have 4 different records of A. diaza in Laguna de Pascual, but I only want to know that that species is present there, not that I've found it 4 times there. So I've done a distinct clause in here to only return unique combinations of species and basins. Which basins contain which species? Okay, that's taking the same, sorry, I got one. The previous one is taking this one and basically ordering it the other way round. So if I'm asked which basins contain which species, I return a list of basins, ordered list of basins with each species in the second column, whereas I want to know which basin does each species occur. On the left, I lead with my species and then put in the second column my basins. Yeah? Now, see what I'm saying there? It's just different ways of presenting the same information to answer slightly different questions. And when you ask a question in your assignment, think which is the best way to present this information. If you're presenting the same information, but it's just ordered differently and therefore is read easy, it's easier to answer different questions the way the data is ordered in the table. Which basins contain which species? Yes, that's the same one. So we're just doing a within, but we're returning distinct basin species combinations, and we're ordering by the basin rather than the species. Okay, let's go back to remember that bounding box query. Okay, let's actually get the river lines that actually intersect the basin, the Mexico basin itself. So I've got a new view. Mexico intersect rivers. So this is giving me river lines that intersect the basin and where the basin is Lake Texcoco. So this is a true spatial query. And in this case, this is the result that I get. Okay, I've lost some of the ones around the outside with the intersects of the bounding boxes, but I've still got one line here, at least, which is well outside of the basin, but the spatial relationship saying it's actually intersecting with this basin. So some part of this line, wherever this line starts and stops, is going into this polygon for whatever reason. Now, if you know anything about rivers and watersheds, you should know that that's impossible. Rivers don't flow over watersheds and into other river basins, or usually don't. There are a couple of instances where it is. This is in fact, the reason why it's doing this is in fact because it's to do with the engineering, the water engineering of Mexico City, and this connection has been physically dug to get rid of wastewater out of the closed Mexican basin. It's basically that's an artificial river that's been created. Anyway. Okay, but I don't want that. I just want the actual bits of the river which are actually inside the basin. Okay, so what have I got to do? Well, can use a geometry processing function as opposed to a query function to return the bits of the geometry that are within the basin. So in this case, instead of I can do the intersects command just to return the lines that intersect the basin polygon. But I want to clip any lines with the edge of the basin. Yep. So what I can use is the intersection function, which gives me the part of the geometry that matches anywhere clause here. So I am saying, give me the intersection of the river and the basin geometry for all the lines that intersect the basin and where the basin is the Lago Texcoco. So it's basically clipping all the part of the polygon, part of the line that is outside of the basin polygon. So we end up with a little clipped section now. Hey, brilliant. So we now know the architecture of PostGIS. So we know how its relationship to the Postgres database, the fact that it's an extension that sits inside it, basically. But we also know that a lot of the functionality is maintained by calling these external libraries written in various languages. And that if you don't have the external libraries, PostGIS don't work. It's a sort of shell, basically, without having those libraries attached to it. We've seen the syntax of PostGIS Spatial SQL, and we've seen how we can map the results of queries within QGIS, and we've seen how I shouldn't really need to tell you this, how important it is to understand, to check the results of your queries and make sure that they've done what you expect them to do and that the data is in fact behaving like you thought it should behave. That instance where I had that empty row for the ecologies, the data appeared absolutely fine when I looked at it before it was imported, but it was the import process itself that resulted in this artifact of the extra row. So always check what you're doing, and especially with Spatial SQL, where it's very easy to think you've written the right result, a query that returns what you hope to return, but the reality is that there's something in your query that's wrong and it can result in incorrect results. So I do thoroughly recommend checking your queries visually in QGIS. Or the alternative is to do the same analysis in something like ArcMap or something like that, and then compare the number of rows. But it's not, I would just do it in QGIS, make sure everything's all right. When it comes to development, writing Spatial SQL is quicker. Once you get used to it, it's quicker and often more powerful than using graphical interface-based query. So in one query there, in a few lines of code, we can undertake a query that might involve 5, 6 GUI windows in ArcGIS or in QGIS to actually perform. You might be doing 3 different attribute queries, a couple of spatial attribute, spatial, whatever you call them, query by spatial location or whatever they call it in ArcGIS. You may be doing a summary on a statistic on a return table. So it's much, much quicker if you can write the stuff, and allows you to do much more powerful stuff on the fly. And yeah, well, and these views, desktop GIS are garbage. They don't really support views at all, not that I'm aware of onto spatial data like you can do with Spatial SQL. There's no such thing. I can't create a complex spatial query in ArcGIS, not without these. There are ways to do it with the sort of enterprise extensions and things like that, which provide a spatial SQL type of interface in Esri. I mean, it does exist, but you have to pay extra money for it. But certainly in ArcMap, if you're just a basic ArcMap user, there is no equivalent to the sort of dynamic spatial views onto the data, apart from your simple, select, what are they called? Feature layer definition queries, basically. You can do those simple